exam. Like, you remember that our exam with the request has been made for, this wasn't actually from your review per se, but from the homework. So this is exercise 5.2.1e. Okay. So what it tells us is we have x has a normal distribution with 3.2 and variance 6.5. Y has a normal distribution with negative 2.1 and 3.5. And Z has a normal distribution with 12 and 7.5. And they are independent random variables. For E, we're supposed to find the probability that the absolute value of x plus 6y plus z is greater than or equal to z, or greater than or equal to 2. Now again, I told you on this that when you look at the solutions manual, it makes this look really complicated. Okay? But we're not going to make it complicated. We're just going to say, okay, well, I have a new random variable, and I'm going to call it w, which is x plus 6y plus z. Let's say that's my new random variable. Okay, what I need to do is I need to find the new mean. Okay, so to find the new mean, okay, well, let's write it as the expected value of x plus 6y plus z, and just use our rules for expected value that we memorized a while ago. So this is the expected value of x plus 6 times the expected value of y plus the expected value of z. Correct? That's what makes sense to do for our expected values. So this is 3.2 plus 6 times negative 2.1 plus 12. So 2.6. And we need to find the standard deviation for w. It's usually easier if we start by finding the variance for w first, because we know the variance rules. So this is the variance of x plus 6y plus z. Okay, so what happens with our variance? We know that if they're independent random variables, which they are, we can just add the variances. So this would be the variance of x plus, what happens with my 6? It comes out as a 6 squared. Variance of y plus variance of z. Let's see, so my variance for x was 6.5, variance for y was 3.5, oh, but I was supposed to times it by 6 squared, and variance of z was 7.5. So 140 is my new variance, but I also need to find my new standard deviation. So I just take the square root of the variance. So 11.832. Now again, when I do these problems, I think I find it easiest to kind of do it step by step. So the first thing I do is I find my new mean and my new variance just by using our old rules. And then I try and use what I know about the normal distribution. Okay. So according to what we learned in section 5.2, we know that any combination of normal random variables, any linear combination, is still going to be normally distributed. So W is still going to be normal. And we found the new mean and the new variance. Once we know our new mean and variance, now let's try and find the probability. So instead of the absolute value of x plus 6y plus c, let's rewrite it as the probability of the absolute value of w is greater than or equal to 2. Once I write it like this, do you know how to find that probability from section 5.1? And it doesn't look so complicated anymore. How did we find this probability yesterday when we were talking about section 5.1? I wanted to first get rid of the absolute value. So if the absolute value of W is greater than or equal to 2. So like here's my 2, here's my negative 2. Am I looking for the area in between or the area on the outsides? Outsides, because the absolute value is greater than or equal to 2. So I'm looking for the probability that W is less than or equal to negative 2, or W is greater than or equal to positive 2. Before I can do this, I need to standardize. So it's going to be W minus the mean of W over the standard deviation of W. Okay. Is less than or equal to negative 2. Or W minus the mean of W over standard deviation of W is greater than or equal to, oh, what did I miss? I forgot to actually standardize the number. So negative 2 minus my mean of 2.6 divided by my standard deviation of 11.832. And 2 minus 2.6 divided by 11.832. Okay. So this is going to be the probability that Z is less than or equal to negative 0.39, or Z is greater than or equal to negative 0.05. Okay. Now, have you guys found anything wrong in my work so far? And so if I was to draw a new graph with my actual Z values, these are my Z values, so I want less than or equal to negative 0.39, okay, or greater than or equal to negative 0.05. Okay. So if I look up negative 0.39 on my Z table, it gives me 0.3483. Okay. If I look up negative 0.05 on my Z table, it gives me 0.4801. But that's the area to the left, and I want the area to the right. So I need to do a 1 minus the 0.4801, which gives me 0.5199. Okay, so this total probability over here is 0.3483 plus 0.5199. Which gives me 0.8682. You'll notice in the solutions manual that they have a 0.8689, which probably means that they just didn't have to round their Z values to use the table. They probably used the computer. Okay. So, questions on this problem? Okay. Again, what we learned from this problem is you start off with something that looks really nasty. Ignore it for a minute. Just look at, say I have a new random variable W, find your new mean, your new standard deviation, and then just write it as the probability that absolute value of W is greater than or equal to 2, and it suddenly looks a lot simpler. At least I think it does. So, questions here?
Could you run through how you got that 2.4 or 0.3483?
Oh, 0.3483. So my Z value is negative 0.39, and I was looking for the area to the left. Okay. So if I go to my Z table, I'm looking for negative 0.39. So negative 0.3 down the side, and then go across to the 0.09 in the hundredths place. Gives me my 0.3483. Okay. And then when I try and look at my 0.05, I go to my negative 0.00 or 0.0, and then go across to the 5 hundredths place. Gives me that the area to the left of that was 0.4801, and I did a 1 minus that.
Is that showing this to the left?
Yep, because this always shows the area to the left.
And this table will be included on the exam?
This table will be included on the exam. Okay. I will ask you though, but as far as review for the exam, we'll do 5.1.4 G. Okay. So what this problem tells us is that we have the x's normally distributed with a mean of -7 and a variance of 14. And for G, we want to find the value of x for which the probability that x is greater than or equal to that specific value is 0.27. Okay. Now, for the test, I will probably give this to you in like story format. Okay, so we'll maybe pick one of those after this to do. So find the value of x for which this is true. So what that means is I want the area in the right to be equal to 0.27. Okay. Now, I don't have a table for a normal distribution of -7 and 14, but I do have a table for the z distribution for my standard normal. So what I'm going to do, okay, sorry, I like to put my areas above my curve. So I want the area to the right to be 0.27, and I'm looking for, first step is I have to find the specific z value that will make that work, because I only have a z table. Now my z table only has areas to the left. This is an area to the right, so I should use the complement rule. Say if the area to the right is 0.27, then 1 minus 0.27 is 0.73. So the area to the left is 0.73. So what I'm going to do is I'm going to look on the z table and try and find 0.73 as an area. Now remember, your areas or your probabilities are in the middle of the table. So I'm looking for 0.73 in the middle. So 0.73 looks like the closest I can come is this 0.7291. Okay, which means that my associated z value is 0.61. So I get my ones and tens place from this column and my hundredths from the top. So z, the z value that makes that work is 0.61. But they didn't ask me for a z value, they wanted me to tell them the x value. So I need to work backwards. I say, well, I know the formula for this is z equals x minus the mean over the standard deviation. So we plug everything in. So we know z is 0.61. X is what I'm looking for. My mean is -7. And my standard deviation is what? Square root of 14. And solve for x. So first I have to multiply by the square root of 14, and then that minus the negative became a positive, so I'm actually going to subtract 7. So negative 4.717. Okay. And the book technically has negative 4.7071. Why is it just a little bit different? Okay. Because when we looked it up, we couldn't find 0.73 on the table exactly. But they used the computer, so they got a more precise z value, and they then got a more precise x value. But since we can't give you computers for the exams, we get to learn how to use tables in class. That's the only reason we still use tables, I think. Now, let's see.
Could we do a binomial distribution problem?
Yep. So I can guarantee that binomial will be on the test.
Oh.
Okay. So that's a good thing to want to do. So if we go to the supplementary problems. So I was going to tell you, so make sure that we learned our 3 discrete distributions that I told you we need to know. So the binomial, geometric, and negative binomial. Make sure for the test that you write down the formulas for those, like if you know the CDF for it, if you know the expected value or the variance, like everything I told you about those, make sure you have those on your cheat sheet. for the test, for all three of those distributions. Okay.
What were the binomials?
So our discrete distributions are binomial, geometric, and negative binomial. Okay. Now there were more discrete distributions. There are also continuous distributions, but these are the only three discrete distributions I'm going to make you do for the test. Okay. So you need to know those three, and you need to know the normal, and those are the only specific distributions that I'll make you use on the test. So as far as a binomial problem to do, well, we can do like 3.8.1. Now, I don't know if you remember, but when we learned about the discrete distributions, we didn't finish the handout, and the handout had like section 3.8, and I wrote in a bunch of word problems. If you're having trouble with the discrete distributions, go through that handout as well. It'll just give you extra practice. Okay. But 3.8.1, an integrated circuit manufacturer produces wafers that contains 18 chips. Okay. Each chip has a probability of 0.085 of not being correct. Okay. So for part A, find the probability that a wafer contains at least 3 incorrectly placed chips. So probability that x is greater than or equal to 3. Okay. So first of all, you have to go through and you have to say, is this a distribution that we know how to work with? Okay. So for binomial, you start by asking, do we know in advance how many chips we look at? There are 18. Okay, is the probability constant? Are they independent? And is each one either a yes or no kind of answer? Okay, so this seems to fit everything. So this is going to be binomial. Let me erase that for a second. With n equals 18, p equals 0.085.
Sorry, can you repeat why you say it was binomial?
What?
Can you repeat why you said
Oh, why? So the three things for binomial is you have to have in advance the number of trials. And we know that we're only looking at 18 chips. Okay. You have to have your probability of success stay constant for each chip. And they told us that each chip has a probability of 0.085. So this is a constant probability. Okay. And each chip should be independent of the other chips. And it doesn't actually say that specifically, but it does say that each chip has this constant probability, which does kind of imply that they are independent of each other, because otherwise the probabilities would change. And the last condition is that, what, do you remember? It has to be either a success or failure. So only like two options. So in this case, we could have correct or incorrect. Although technically incorrects are our successes at the moment. Okay, and so it meets all four of those categories or qualifications. Okay, now just in case, so remember, what is the only difference in the qualifications between like binomial and geometric? Which one of these things doesn't hold? Okay, that one is actually still true for the geometric. The only thing that changes for geometric is this fixed sample size. So for the geometric, you don't know in advance how many trials you do. You stop when you get your first success. And the negative binomial is you stop when you get your rth success, so like your third success or fourth success. So you don't know in advance n. So that's the difference between the three distributions. Everything else stays the same. So we know it's binomial. Now we're looking for the probability that x is greater than or equal to 3. Now to find this probability, well, what x values are greater than or equal to 3? I would have to do the probability that x equals 3 plus the probability that x equals 4 plus all the way up to the probability that x equals 18, correct? Is there an easier way that you can think of to do this?
1 minus, go down.
Okay, 1 minus, use the complement rule. So which probabilities do I need? I need 1, 2, and 0. Okay, so for the binomial distribution, a 0 is possible because it's possible that they could put 0 in correct chips. Now when you think about the geometric distribution, you stop when you get your first success. So if you have to get at least one success, you have to try at least once. So you only start at 1. For a negative binomial, if you need to get 5 successes, you have to try at least 5 times.
So the only one that includes 0 is the geometric one?
The binomial, yeah. It's the only one that includes our 0. Okay. So at this point, we need to find these probabilities. To do that, it would probably be useful if we remembered the formula for a binomial probability. Okay, for a binomial probability, the probability that x equals k, or little x, or whatever you want to do, okay, is n choose k, p to the k, 1 minus p to the n minus k. So remember, this p to the k is the probability of getting k successes. 1 minus p to the n minus k is the probability of getting the n minus k failures. And what does this part do? It's the combination. It counts for the number of ways that I can get that many successes. So we need to do this for each one of those x values. So the first one, n is 18, so we have 18, choose 1 success, times the probability of success is 0.085, and I need 1 success. Then the probability of failure is 1 minus 0.085, and I need, if I have 1 success, I need how many failures? 17. Okay, plus, and now we do everything again for the 2. So 18 choose 2, 0.085 to the power of 2, 1 minus 0.085 to the power of 16. Because if I have 2 successes, I need 16 failures. And we need to do it for the 0. Okay. So it'll be 0.085 to the power of 0, and 1 minus 0.085 to the power of 18. Okay, because I'll need 18 failures. And at this point, I put in my calculator, and it does take a little while, which makes you really appreciate having a normal approximation, and the reason why we want normal approximations. So the 3 probabilities that I get are 0.3379, 0.2668, 0.2021. Okay. Did you guys get those probabilities? So I get that my total probability of 1 minus all of those is 0.193097. Anyone else? .21. Okay. Anyone else get the same thing that I did? Okay, did you only round to like 4 decimal places maybe? Did you? Okay, so I got my thing twice, so we'll go with that. Okay, so any questions on this?
It's just kind of using the calculator. Like, what's the difference between NCR and NPR? Like, when
So using the calculator, we have NPR and NCR. Okay, anyone want to answer that question?
Order matters, right?
Okay. So we use this if we have a permutation, which is when order matters. And we use this one if we have a combination, which is when order doesn't matter.
What order exactly? The way that they are.
Yeah, so this is in section 1.7, if you feel like you need to review these, but when we say order doesn't matter, let's talk about, okay, well, let's stick with the same problem, okay? So if I wanted to have 3 incorrectly placed chips, okay, out of my 18 chips, that could be like, and the first one could be incorrect, the second one could be incorrect, third one incorrect, and then the rest could be correct, 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 etc. Okay, and that would give you 3 incorrectly placed chips. But could I also do an incorrect, correct, correct, incorrect, correct, incorrect, and then all the rest corrects? That would still give me x equals 3. Okay, so when we say order matters or doesn't matter, we say, okay, well, when you're done, when you're counting these, do you count these two things as the same thing? Like, so do you care about the specific order of incorrect, correct, or incorrect, or do you just care that overall there were 3 incorrect chips? Okay, so in this problem, we just want to know if the wafer has 3 incorrect chips. We don't really care which order they were correct or incorrect in. Okay. What is something where the order does matter? Like, can you think of a good example where order would matter? Okay, so like if we're doing a race, first, second, and third place, the order specifically would matter because it makes a difference if it's John, Julie, Stephen, or Stephen, Julie, John, stuff like that. Okay, or if you're picking pins for an ATM. So if I ask you how many possible pins are there for an ATM, 4-digit pins, well, changing the order of your pins, that's going to make a difference. If you punch your pin in the wrong order, does the ATM give you money? Okay, no, and so that's something where order would matter. Okay. But it's just things when you go through and you say, well, is the order I punch the numbers in going to make a difference in this scenario?
So in binomial, now what's it called, binomial?
Binomial distribution.
Does it, do we have many permutations?
Nope. By definition, binomial has to be combinations. Order doesn't matter. If you're ever given a scenario where the order would matter, it wouldn't be a binomial distribution. So the binomial distribution always just counts your successes, so it just counts that there's 3 chips, and it never cares about the order that the chips are in. Okay. Continuing this problem, like B asks, what is the probability that a wafer contains no more than 1 incorrectly placed chip? If we want no more than 1, that means x is less than or equal to 1, which would be the probability that x equals 0 plus the probability that x equals 1. Now, do I need to refine these probabilities? No, we already found these probabilities, right? These two probabilities are, let's see, this one was 0.337948, and the 01 was 0.202106. Correct? Did I transfer those correctly? So 0.540053. Okay. And for C, other things I might ask you is like, what is the expected value? Or what is the mean number of chips? Or what is the expected number of chips? I might ask you anything like that. For the binomial, remember that there's the formula, n times p, which you'll want to have written down somewhere on your sheet. So n is 18, p is what, 0.085? Yep. So 18 times 0.085. So the mean is 1.53. So I expect to get about 1.5 misplaced chips per wafer. Okay. Now obviously on any given wafer you can't have 1.5 incorrectly placed chips, but the average, if I look at mini chips, is 1.5 misplaced chips per wafer. Now the problem doesn't ask you for the variance, but I might on the test, I might ask you to tell me the variance or the standard deviation. So the variance is n times p times 1 minus p. So 18 times 0.085 times 1 minus 0.085. So 1.399. So this is what I might ask you to do for the test for the binomial distribution, is I'm going to ask you a probability. I'm going to probably ask you the expected value and probably ask you the variance or standard deviation. Now, I will not tell you on the test that it is a binomial distribution. You need to have written down these are the steps for binomial distribution and be able to recognize it. So any questions here on the binomial? So we have a sample of 10 fibers from a collection of, let's see, so our total is 92 fibers. We have 43 fibers of polymer A, 17 fibers of B, and 32 fibers of C. So this is my pool from which to draw, and it appears that we are drawing 10 fibers overall. Now, looking at this problem, you would have to decide whether or not you're putting things back. I'm going to guess that we're not putting stuff back, just the way that it's worded. Okay, and specifically since it doesn't say with replacement. So A says, what is the probability that the sample does not contain any fibers of polymer B? So probability of no B's. Okay, so you said you wanted to just do this with straight probabilities. So intuitively, how did you want to do this problem?
Find the probability of A, B, and C, and then
Okay, so this is what I would think of if I was trying to find the straight probability. Is I would say, okay, so if all of them have no B's, then that means the first one is no B, the second one is no B, third one needs to be a no B, etc., all the way up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I do this for 10 of them. Okay, so on the very first one, what is going to be the probability of getting something that is not B? Okay, so not B is 43 plus 32. I guess I could do that in my head. 75. 75 out of our total of 92. So for my very first draw, to get a not B, there are 75 possibilities out of 92. Okay. But on my second draw, how many not B's do I have to choose from? 74 out of 91. My second draw will be 73 out of 91. Next draw, 72 out of 90, 71 out of 89, 70.
We should change this up.
I did 91 twice?
Yeah.
Thanks. Okay, so let's try 73 out of 90, 89, 88, 87. Let's see, so this is going to be 69, 68, 67, 66, 86, 85, 84, 83. Okay. At this point, it's going to take a little while to put in, right? But we can try it.
Could you do like 75 over 92 factorial divided by 65 over 82 factorial?
Okay. Well, if I do 75 factorial, it's going to do 75 times 74 times all the way down to 66, and then it's going to keep going.
But if you divided it by 65 factorial?
Okay, so you want to do 75 factorial over 65 factorial?
And does that work?
Yes, that should work. Okay, so that might be faster to try that. And then 92 factorial over 83 factorial. No, 82. Okay, so maybe someone tried the long way. I'll try it this way. Let's see if we get the same answers. Oh, I think it believes that is too big to work with.
It says overflow or something like that.
Yeah, so I keep getting math errors. So this is too big to even put in my calculator. Okay, so then let's try a different method. Okay, because you said you wanted to just try the straight probability and the book was using the combinations. So let's look at what the book has and see if we can figure out why this appears to be the same thing. Okay, so the book says, or the solutions manual, we say, okay, well, we want to get no B's. Okay, and we assume on this the order doesn't matter. Like, we're just drawing fibers out of the bag. We probably don't care which fiber we draw first or second. Okay, and so we say, okay, well, I need to choose 10 fibers that are not B. Okay, how many fibers are not B to start with? There are 75 not B fibers, and I need to choose 10 of them. Correct? So this is to get not B's. And then we say, okay, well, that's just the number of ways to get not B. But you need to divide that by the total number of samples. So for the total number of samples, you'd say, okay, there were, what, 92? 92 total fibers, and I was choosing 10 of them. So if I wanted to do it just this way, I say, okay, what's the total number of samples I could choose, and then what was the number of ways to choose something that is not B? So number of ways to choose something that's not B, number of total samples. So hopefully I can put this in my calculator. Okay, and it will actually give me an answer. It gives me 0.1149. Okay. Now, so this was using a combination. Now, if you actually work this out, okay, and use the combination formula. So this is 75 factorial over 10 factorial times 75 minus 10 factorial. Okay, over 92 factorial over 10 factorial times 92 minus 10 factorial. Okay, what are those 10 factorials going to do? They cancel, and we get 75 factorial over 65 factorial, okay, times, let's see, 82 factorial over 92 factorial. And when you start simplifying this, you actually get 75 out of 92 times 74 out of 91, down to 66 over 83. Okay, which, notice, is the same thing we tried to do intuitively, but it did make it so it was big enough that I could, small enough I could put it in my calculator. Okay, so as far as the test, you may do it this way, or you may do it the second way, and I will make it small enough that either way will be something you can put into your calculator. Does that answer your question of why you want to do it that way, but the book did these combinations? Okay.